Hey, welcome to Ones and Zeros. My name's Ben, and today we are looking at another episode of our Unearthing C++ series. This will be episode 7 of the series, and in this one we're going to be taking a look at structures and the ways you go about creating them, how they're used, some of the difference between structures and classes, as well as some of the ways that you can actually optimize structures to make sure they're not going to be consuming more memory than you want them to effectively. So we are going to be using Visual Studio for this one, much as what we've used in the previous episodes of the series, just to keep things nice and simple so we can just focus on the code that we're working with and not anything additional. And let's take a look at what a structure actually is. So you can think of a structure as being almost like a box that you can store multiple different variables in of different types. The different variables can be different sizes. You can have variables containing text and others containing different types of numbers and things like that. So they can be really useful in a situation where you need to group a bunch of different variables together for a particular purpose, and even in a situation where you may then create an array of structures to create to hold sets of values in an array. So let's look at a bit of a simple example. So let's pretend that we've got something that we're going to be using to render stuff to the screen, and we need to be able to store an X and a Y coordinate together so that they're both in one little package that we can use in various parts of our program. So we'll go through and we'll actually create a struct, and let's call this vec2 struct. And let's pop in a couple of int values in there, and we'll call this one ipos A and ipos B, with the little I at the front letting us know that those members are both integers, and then change these to X and Y would make more sense, our X position and our Y position. So that kind of defines that as a type. You may see, if you watch some of my STM32 videos, that I will do a type def struct, which is not explicitly necessary in C++. It will still work, but it'll do the same thing as just defining the struct normally. So we'll have a little bit of a look at kind of how that works, and that's more a leftover from me doing a lot of C programming and just doing it by muscle memory effectively. So we've got our structure, we've defined the different types of values that it holds, which these guys are known as members of the structure because they belong to it. And we can then go through and say if we wanted to have two sets of coordinates that we wanted to store, we can go through and create those. So tell it that vec2 struct is the type that we want to store, and we'll go coordinate A and coordinate B. Now we can initialize these much like any other variable when we create them, and similar to when we initialize an array in the declaration, we can just use the squiggly brackets and say we can put -10 and 20 for that one, and we could put 100 and 200 for that one, for example. So that's got our structures defined. We can print out those values to make sure that they're actually working the way that we want them to. So we'll just go coordinate A, position X, or actually X position, make more sense, and we'll go coord A, and then I'll put a dot, which gives us access to the members of that structure, and we'll go ipos X, and then we'll go Y position, and coord a ipos y. And we'll chuck an end line at the end of that one, so that'll display the coordinates from our first structure. And let's go through and just copy and paste that, and we'll do the same thing for our second one as well. If we hit F5 on that one, we'll get those values printing out that we've defined in there. And much like we've initialized these with values in them, we can write values into them as well, just as we would normally. We can do it individually, so access the members individually and write to them, similar to the way we've read from the members individually down here. So in this case, if we wanted to put -20 and 40 in there, and we put -20 and do our y coordinate. And similarly, we can also do it as a group as well, where we could go 200 and 400. Again, we'll just use double the values we used for initialization. So allows us to access the members individually or be able to write to them as a whole, which makes it quite convenient. And again, if we just run that, we'll see that those values will be updated like so. Now, structures and classes do share quite a fair few similarities. The main difference being that members of a structure will typically default to being publicly visible by things that are outside the structure, whereas a class will typically default to its members being private so that they're not accessible from outside the structure. And we can define certain aspects of it as being public and private, which is something that we will take a bit of a look at in a future video. Structures can also contain functionality, so we can put functions and operators inside a structure, similar to we can with a class. So they're fairly similar in that regard. I do try to limit the sort of functionality that I personally put in a structure, simply because even though they're quite similar, I like to make sure that they're both being given specific jobs to do, so that there's a reason why I would use one or the other. And it also tends to help visually when I'm going through the code and trying to debug, especially if I've got, 1,000 or more lines inside a particular header or source file. So with a structure, I generally will treat that just as a container to store data, whereas a class is something that I will generally go for if it's something that needs to contain functionality. So similar to if you've seen some of the drivers that we've written in some of our STM32 videos, I'll typically use a structure to store a set of data that we might use to initialize a driver. Whereas the actual driver itself, because that contains functionality rather than just a set of data, I'll use a class for that. So you can kind of do some stuff one way or the other, depending on your particular coding style. That's just the approach that I prefer to take when dealing with structures. Like I said, just a box to store groups of data in, like we've done here. I do like to use operators with structures sometimes, and we will have a video on operators coming up in future where we kind of take a look at why we would use those and how they can be really useful for structures. But for the moment, we'll keep it simple for this video. The one other thing that I did kind of want to go over in this video is taking a look at keeping data optimized inside a structure. So let's delete what we've got here for the moment. And we're going to create a structure and we'll call it mixed data struct. And I'm going to just modify its name there, so mixed data struct unpacked. Now, we're going to use some different data types in here. So say, for example, we wanted to have a character in there storing some data. And we wanted to have, say, a uint. Let's go with a uint32, so a 32-bit unsigned integer. And we'll call that udata32a. And then we wanted to have a uint8, so a single byte, in this case an unsigned 8-bit value. We'll call that udata8a. And then we might want uint16. Call that data16a, and then another uint32. Call that udata32b, and then just for the sake of it, we'll pop in another. Might actually just copy down our uint16 there. So in this case, the way we've ordered the particular pieces of data inside the structure is fairly inefficient. The reason for that is because the data inside the structure is going to be stored in chunks that are the size of the largest type of data that we're storing in there. So in this case, the largest type of data we're storing here is the 32-bit unsigned integers, which means that it's going to store the variables in blocks of 32. So if we take a look at how big that actually is when the compiler's done what it needs to do. The size of mixed data struct unpacked. And we'll pop an end line there as well. And we run that, it will let us know how big that is. So that's taking up 20 bytes to store that data. Now, if we close that and we have a look at the size of these individual bits of data, this is 1 byte because it's just a single character. This will be 4 bytes because it's a 32-bit value. This will be 1 byte. This will be 4 bytes. And this will be 2 bytes, 16-bit value. So if we add all of those up, we can see that there's actually 12 bytes worth of data being stored in that structure, but that structure itself is taking up 20 bytes worth of storage space. And that's why we've given it the name unpacked, because there's a bunch of padding in there in order to make sure that all of the data is 32-bit aligned or 4-byte aligned, because the largest type of variable we're using in there is 32 bits or 4 bytes. Now, we can save a bunch of memory simply by the particular way that we order the structure. So if we create another one that's mixed data struct packed, and we go through and let's start with our biggest items first. So udata32a and udata32b, and then we'll go with our uint16 there, which is udata16a, and then our uint8, and our character. Now what we'll do is we'll copy this and I'll get it to print out the size of that one as well. And we'll run that. We can see that our unpacked size is 20 bytes, our packed size is 12 bytes. The reason why that happens is because this fits into 32 bits or 4 bytes. This fits into 32 bits or 4 bytes. This then takes up 2 bytes, but we still have 2 bytes left over of that 4-byte chunk. And the compiler is smart enough to realize it can actually fit 2 8-byte values into the remaining 2 bytes. So this takes up 4 bytes, which means that overall we have 12 bytes because it's able to actually pack these together, and that's what we mean by unpacked and packed. So simply by changing the order of those variables, even though it's containing exactly the same data types and the same amount of data, it's actually using 8 bytes less to be able to store that data because we've been more efficient with how that works. Now, I don't always go through and make sure that I've ordered everything properly to make it packed in some of the code that I'm working on. Part of that is because visually it can sometimes be useful to have certain bits of data grouped together. And that can be really useful, especially when you're designing the software or going through and debugging it and things like that. However, when I go through to actually do an optimization phase on everything, or if I'm in a situation where I need to optimize memory usage, then I will actually go through, and especially if I'm using an array of structures, then I will go through and make sure that things are actually a bit more efficient with how data is being positioned within a structure. And generally the rule of thumb is to make sure that you're going with your largest data types in order down to your smallest ones. We would find, however, that that rule doesn't always hold true because we can do the same thing here. The compiler is still going to figure out that it can still be turned into a 4-byte chunk. And if we run that, even with the change in order, we're still going to get a packed struct size of 12 bytes. Things can be a little bit different if we say we grab our character and we put that at the top, where we'd have 1 byte, 2 bytes, and then another 1 byte, then we're probably not going to see the same 12 bytes being used. We'll now see it's actually 16, because what the compiler will then be doing is it'll have 1 byte followed by 3 bytes worth of padding. Then it'll have these 2 bytes. It knows it can pack this one in with the uint16. And then it would have another byte of padding before it goes to these guys. So straight away, we've got 4 bytes that are being wasted simply because we've changed the order of the data. So it's worth keeping in mind that sort of thing, especially when you're dealing with microcontrollers that have a very limited memory, because by being a little bit more sensible with how you're putting the data in the structures, you can save yourself a bunch of memory. If we had an array of 100 of these structures, then the difference between our unpacked and our packed would be 800 bytes, which is not a tiny amount of memory at the end of the day. So that's kind of the approach to optimization. The other thing that I wanted to sort of cover is the type definitions that you would have seen me using in some of the other videos or in some of the source code that's up on GitHub. And that is basically, like I said, a holdover from C rather than C++, where, say I was doing a type definition of our packed structure here, we could go tell it what we're using to define the type def and then make the name of the type def, like so, which would then create a type definition. The approach that I would typically take is not having the type definition separate to the structure though, where I would actually combine both of those statements together, which means grabbing hold of the name and moving the name down to the bottom here. Now, as I mentioned, that's completely unnecessary in C++. It's just something that I do because it's muscle memory after writing so much C code over the last however many years. And if we run this, it's actually going to do basically an identical thing, because C++ will see it the same as if we just had the struct on its own without the type def. So you don't actually need to have that there. That just wanted to sort of explain that as to why you may see that in my code. So that's kind of what that is, and it's basically a combination of the structure declaration or definition and the type definition combined together in one statement, which is how I would typically approach it in C. So hope you found that interesting. That's a bit about how structures work. Like I said, we will have a video coming up looking at operators, where we'll see how operators can be useful for copying between one structure and another, or doing maths between them. Does make certain things a little bit easier. And we'll also, next video should be looking at classes, followed by the video beyond that being on singleton classes, which is something that you may have seen used quite a bit in the STM32 videos, because I'm a bit of a fan of classes and singleton classes for some things. So that's that one. Would also like to say a huge thank you to all of the people that have liked and subscribed to the channel, and also all of the awesome comments that have been left on all of the videos. And a big thank you to our 2 patrons up there, Craig and Luther. It's really awesome to see people want to help support the channel. If you do want to help support the channel, we do have our address for our Patreon there. There is various benefits that you can get out of that depending on what sort of tier you want to sign up for there. If you've got any questions or comments about this, feel free to leave them below the video, or you can jump onto our subreddit and leave them there as well. Always like reading the comments and seeing what feedback, or if there's video suggestions that people have, things like that as well. And if you want to check out the source code from some of our other video series and things like that, there is also the link to our GitHub there as well. So hope you're having a wonderful day or night or evening or morning, whatever it is when you're watching this in your part of the world. And thanks for watching.